It's day 10 of 50 days of tutelage. We have really come so far. Now, today we're going to be talking about sets and Venn diagram. It's one of the major topics in mathematics, and students often find it difficult to make proper interpretation of these. So, I'm going to be starting with the definition of set. So, what is the mathematical definition of set? We define set as a well-defined collection of distinct objects. So listen to those statements there. So if you say something is a set, then it is a collection. It is a collection. This collection is well defined. And why is it well defined? It is well defined such that you cannot have, it cannot be ambiguous, such that if you say this is set of so thing, you should already know what you will find in that set. Then you shouldn't be saying that, oh, this belongs to the set, and then whereas this does not belong to the set. For instance, if I have a set and this set is containing A, B, C, 1, 2, 3. Now, this set, I have to properly define it. So if I say this is a set of English alphabets, it is not well defined. Or if I say this is a set of some natural numbers, it is not well defined. So I have to find a way to properly define it such that anybody who does not even have access to see what I've written here, they can also reproduce the same set and there would not be any problem. So a set is a well-defined collection. And not only that, it contains distinct objects or otherwise known as distinct elements, meaning that you cannot have two things that are the same. So if you already have the element there as one, then you cannot have the element there again, repeating itself. So no repetition is allowed in the proper in a set. So that is the definition part. Now, you need to understand that for different sets, which I'm going to be describing in this place, we have two major ways which a set can be described. We have what we call the roster form, and then we have what we call the set builder form. So I can define a set. Let's just say a set, and I say the set contains, let's say the set is set S, and it contains 1, 2, 3, 4, 5. Now, I can also define another one. I can say S equals, let's say, 4, let's say 9, let's say 16, let's say 25. Now, these are set, and I've listed all the members that are there now. Now, if I want to have more in this place now, that means that I will continue to list and list and list and list. But there's a better way you can do this using what we call the set builder form. So this form is a roster form. You list every element that are present in the set. But there's what we call builder form. Builder form is a way of trying to use a definition, something that is going to be an umbrella rule that governs every element of that set. So instead of you having to list everything, you just use one thing. For example, I can define okay, let me call this one S1, let me call this one S2. I can define set 1 using so many things. So I can say set S is all x that are natural number. If you have been following our class from the beginning, this should not be strange to you. You know what natural numbers are. All natural numbers such that x is a natural number such that x is less than or equal to 5. So if you look at this definition now, I've already made everything compact. Number one, I'm saying that any member of this set will be a natural number. That's the first thing. But what are those natural numbers? I'm talking about natural numbers that are less than or equal to 5. And you know that the natural numbers that are less than or equal to 5, they are 1, 2, 3, 4, and 5. So this also still describes this set. There are so many other ways you can actually describe this set, but this is just a simple way of describing the set. So you can also say S1 it belongs to the set of integers, but integers such that 1 is less than or equal to x less than or equal to 5. Even this particular inequality, I can still make it such that I will say 0 is less than x less than 6. It's still the same thing because I've restricted it to being an integer. Now, why do I have to even put the number, this set of number that they belong to? If I just say any number less than or equal to 5, and I do not put natural number there, or I just say 1 less than or equal to x less than or equals to 5, do you know that in between these we have 1.1, 1.2, 1.002, 1.004, and a lot like that. So, and that means that I'm referring to real numbers. So I'm restricting it to natural numbers and integers because those ones they always take a step of one as they go to the next guy. So it is easy for me to just say 1, 2, 3, 4, 5. Now look at set 2. Set 2 should look familiar to you. So set 2 is looking like x that belongs to a set of, now look at this now. So if you look at it, looks familiar. It looks like we have a square of 2, a square of 3, a square of 4, and a square of 5. So you want to define this such that set x equals x raised to power 2, such that x is an integer. X is an integer. You can also make it natural number. X is an integer, and 2 is less than or equal to x less than or equal to 5. So look at what I've just defined in this place. I'm saying that set 2 contains anything x squared. But this x squared, I'm describing it such that number 1, it's an integer. And number 2, 2 is less than or equal to x less than or equal to 5. So all I just need to do is what? Always pick numbers from here. So I'll pick 2, I'll square it. I'll pick 3, I'll square it. So this is good. The builder form is good if, let's say, this number now, this list, I listed it from 4, 9, let's say I listed it to 100 or even like 10,000. So instead of you having to like list all the members from 4 to 10,000, you can just say 2 less than or equal to x less than or equal to 100. With this, you have covered everything. That is all x squared that are integers, all x squared such that x is an integer and 2 is less than or equal to x less than or equal to 100. By the way, like I said, if you don't get some things here, you need to go back to the previous class and check. You always see it in the playlist for the 50 days of tutelage. So let's proceed. Now that we have described the way sets are, let's talk about some type of sets. I'm not going to be talking too much about all of them. I'm just going to be discussing the major ones. So we have types of sets. The first one I'm going to be talking about is the empty set. There's something we call empty set. It's also called the null set. So from the name, it is a null set, a set that contains nothing. A set that contains nothing. It is either denoted using this symbol or using this symbol phi. Some students make mistake and they define the empty set like this. No, this is wrong. This is wrong. This is no longer an empty set. So it's either you use this or you use this. You don't use both together. So empty set is a set that contains nothing. Now we also have what we call a finite set. A finite set. From the way the name appears, finite means countable. So finite means that it has an ending. Actually, that's the better way to put it. Finite means it has an ending. That means that you can easily pinpoint the beginning of the set and the ending of the set. So it does not just go on and on and on and on like that. Unlike the set of natural number, like I've defined for you earlier, set of natural numbers, it is infinite. Set of real number, it is also infinite. So a finite set is a set that has an ending. So that's just a summary. If it is finite, it has an ending. It doesn't just proceed and proceed all like that. So we have finite set. We have infinite set is the opposite. Infinite set does not have any ending. Example, all those set of numbers that I gave you earlier, natural number, integers, real numbers, irrational numbers. So we have them, they are infinite sets. Now, the next one we have what we call the singleton set. Singleton. The singleton set. Now, what's a singleton set rather? So from the way the name sounds, it means a set that has only one element. a set that has only one element. And a perfect example of that is a set of prime number that is even. A set of even prime number. A set of even prime number. So you know that that set has only two as its member. So a set of even prime number is a singleton set because it contains only one element. It contains only one element. So we have another one. We have what we call subset. We have subset. What is a subset? From the name subset, a sub of a set, meaning there is a lesser set which is contained in another set. So we say that a set A is a subset of another set B. So this symbol here is the symbol for subset. We say A is a subset of B if it happens that X belongs to A, implies that X belongs to B. So meaning that anything that belongs to A will definitely belong to B. So in that situation, we say A is a subset of B. Now, is it about being bigger that makes somebody to have another set as a subset? Not necessarily. For example, if I give you this instance, let me give you two instances. Let's say you have A here, and you have 1, 2, 3, and you have B here, you have 2, 3, 4, 6, 8. And let's say you have A here, also 1, 2, 3, and let's say you have B here. So let me make this one A1, B1. Let this one be A2, B2, and you have 2, 3, 4, 1. Now, let's see which case is A subset of B. In the first case, 1 is a member of this set A1, but 1 is not to be found here. I don't need to proceed to do anything again. I can conclude that A1 is not a subset of the set B. So it's not about being smaller in quantity that makes you a subset automatically. It has to be that everything that is found in you can be found in that thing as well. Then you say you are a subset of that other set. So, and you can see in A2 now, A2 is actually a subset of B because you can find one here, you can find one here, you can find two here, you can find two here, you can find three here, you can find three here. So that is a subset of that. Now, there's something we call improper subset, and if A is a subset of B, and at the same time B is a subset of A, the implication is that A and B must be the same. I'm going to put it into perspective. I mean that everything in A is in B, and everything in B is in A. So when you have such thing, then you have what we call improper subset. So that is they contain each other. They can easily contain each other, so they can switch places. I'm going to give you a perspective. So if you have ever like had ice cream before, and then let's say you bought ice cream like of the same size with you and your friend, and if you're Nigerian like me, one thing about ice cream container is that we don't throw them away. There is always a use for them. So what happens is that you notice that you can easily stack them inside each other. Now, this might not be a perfect illustration, but it's just to put into perspective how one set can contain the other, and that other can also contain the particular set in question. So we have what we call improper subset. So that's that about subset. Now, I've also defined equal set as well. Equal set means that everything in A belongs to B, and everything in B also are present in A. Then you have what we call what? Equal set as well. Then we have another one called the universal set. Universal set. Now, what is a universal set? Most students usually get confused about this universal set. You see, the universal set U is not a set of everything, but it has to be specific. For every time we're talking about a set, there is a discussion, that is, there is a matter that we are dealing with, there is something we're trying to address with that set. There's an information we are processing with such set. So, what is now universal set? Universal set is a set that contains all elements in a given discussion. It contains all elements in a given discussion. That's what the universal set is. Now, going forward, there is Another one which is called the power set. The power set. Now, if we have what we call the power set is such that it is a set of sets. Let me call it like that. It is a set of sets. So it's basically the set that contains all the possible subsets of another set. So if I say A contains A, B, and C. So let P of A represent the power set of A. Now, this power set of A will be all the possible, so that is how many sets can you extract from this guy. So we have number one, the trivial subset. In mathematics, we believe that empty set is always a subset of any set. So the empty set is the number one. Then the following is that we can begin to pick singleton sets out of this. We can pick A, you can pick B, you can pick C. Now, after we're done with singleton set, we can start by pairing them into twos. So we have A, comma B, we have A, comma C, and we have B, comma C. I think we're done with the pairing of twos. And finally, you know that we have the fact that this can be equal to itself, that is, each set can contain itself. As long as all the elements in it are present in the other one, then it's a subset. It doesn't have to be bigger. So these are the possible subsets that we have here, and this is called the power set. Now let's look at how many elements do we have here. We have 1, 2, 3, 4, 5, 6, 7, 8. So there's a way to always know the cardinality of this power set. The cardinality, which I will talk about later. So I'm going to talk about that later. But the number of subsets that you can have for a given set, all you need to do is to count the number of things that are there. Here we have how many? 3 elements there. So the power set, we have 2 raised to power 3 elements. Meaning that the power set, the number of subsets that this guy can have is going to be 2 raised to power 3, which is 8. And this is everything that this is all the subsets. These are all the subsets. Sorry about that. So these are all the possible subsets that this particular set A can have. So that's that about subsets. Now let's go to operations of sets. So just like we have addition and subtraction, division and multiplication, we also do some operation on sets as well. So the first one is union. What is union of a set? So if you say A union B, what does it mean to say A union B? It simply means you're talking about X such that X belongs to A or X belongs to B. So that means that we're talking about every element that they are either present in A or they are present in B. They don't have to be present in both of them. And they can also be present in both of them. It doesn't matter. But as long as it is in one, then it is in their union. So it's more like marriage as well. So if a man and a woman get married to each other, the ideal thing is that whatever is in the life of that man and whatever is in the life of that woman, it's present in their marriage, except they are not making it the ideal marriage. So A union B, the union of 2 sets, brings them together such that as long as it belongs to one, then it belongs to the union. So anyways, if you're planning to get married, take note of that. If it belongs to one, it belongs to both. So it's not like my money, my money, your money, our money. It shouldn't be like that. So that is what union of a set, that is what it is like. So now, example of this is, so let's say we have A equals 1, 2, 3. I'm just going to be picking, and B, let's say it has 3, 4, 5. So I'm just going to be picking these simple things. So the union of A and B is going to be 1, 2, 3, 4, 5. So this is the union of A and B. So you can say that there is no repetition because from the first time we had defined that there is nothing like repetition in set. It has to be distinct. So everything is now represented here. The 1, 2, and 3 that are here. So the 3 that was here already has already been represented, but the 4 and 5 that was not there has now been represented in their union. So the next one that followed is the intersection. So what is intersection? Intersection is similar to this union, but this one is everything must belong to A, and at the same time, everything must belong to B. So if you're going to be in the intersection, it's just like saying that, oh, what do we have in common? Exactly. So if you're going to be okay with someone, if you're going to agree with someone, then there must be at least some little things that you guys have in common. So those things that you have in common are said to be in your intersection. So for instance now, so A intersection B, still using the same set I gave earlier, what they have in common is 3. So therefore, A intersection B is a singleton set that contains the element 3. Now, we also have what we call the difference of sets. The difference of sets, that is A minus B. This is actually very, very intuitive. Like, you have to pay attention. So how do you do this? All you need to do is that if you're doing A minus B, just go to A and remove everything that B has in common with A. So for instance, now if I want to do A minus B in this place, what does B have in common with A? That's 3. Remove it. Whatever is left is going to be your A minus B. So we can do B minus A now. B minus A, if you have 3, 4, 5, what A has in common with B is 3. So remove it and repeat what is left. So that's 4, 5. So this is what we call difference of set. We also have what we call symmetric difference. Symmetric difference, that is A, so something like a small triangle is called symmetric difference. It's simply A minus B union B minus A. A minus B union B minus A. This is actually the same thing as A union B minus A intersection B. A union B minus A intersection B. We can easily prove that actually. So let's see, symmetric difference is A minus B union B minus A. So if you want to find the union of this guy now, so what would this be? 1, 2, 4, 5. 1, 2, 4, 5. Now, so if you look at this set, the only thing that is not present here is that if you look at A union B is 1, 2, 3, 4, 5. A intersection B is 3. So the moment I remove this 3, the moment I remove it from there, I have 1, 2, 4, 5. So symmetric difference is also the same as union of set minus their intersection. And then we have what we call the complement of set. Complement of a set. So this one we denote it using either A prime or we use AC here. And what is the complement of a set? It simply means X such that X does not belong to A. So all you have to do is that but this time around, you have to think of the universal set. So X must belong to the universal set. So in this situation, you cannot define complement of a set without considering the universal set. So X such that it belongs to the universal set, but it does not belong to A. So pick every other thing and that will be okay. So let's say my universal set was actually, so I didn't list my universal set here. Let's say my universal set was actually all integers between from 1 to 10 rather. All integers from 1 to 10. So when we say A complement now, so A is 1, 2, 3. So the complement of A will be everything from 4 to 10. So that is what complement is. Complement is simply all things that belong to the universal set but does not belong to that set. So that's what complement is. Now, so let us proceed now. Now that we have done all those set operations, the next thing we want to do is we want to talk about Venn diagrams. We want to talk about Venn diagrams. What are Venn diagrams? Venn diagrams are simply pictorial representation of set information. And I know that the most common one is that you just draw a rectangle and then inside it you just put some circle, you just put some circles. Let me make the circle perfect. You just put some circles, you put some circles, put some circles like that, and you say, oh, this is a Venn diagram. Well, this is correct, but a Venn diagram doesn't necessarily have to always be like this. I can have this as a Venn diagram. Let me try to make a perfect. No, that's not what I want you to do. Well, don't mind that. I wanted to draw a trapezium anyways. So I can represent my universal set like this. This is not bad. And I can say, okay, inside this place, I have a triangle. I can say I have a triangle. I can say I have this. So a Venn diagram does not necessarily have to be like this all the time. It's just that this looks very neat and then this looks very nice. So we don't scatter everything. It's just a pictorial representation. So let's go to how do we actually draw a Venn diagram? There are three things that you need to take note when we're doing the Venn diagram. So the Venn diagram, the Venn diagram. Come in. Venn diagram. So there are three things that we need to take note. The first one is how to identify union. The second one, so the first thing is how to identify union. The second thing is how to identify intersection. And the third thing is how to identify complement of set. Complement of set. So these are the three things that we need to know how to do. Once we know how to do these three things, then Venn diagram is easy for us to represent. So how do you do union? Union is the very, very easy. It is the most easiest of them all. So I'm going to be using three sets. I think I should just use this already. So I'm just going to enlarge this. Yeah, so I just want to enlarge that so that it can properly contain what I'm trying to do. Yeah, so how do we shade union? Let me copy this down so that I can use it for subsequent ones. Now, how do we shade union? Union does not really care about any other thing. For instance, if I want to shade A union B here, if I want to shade A union B, all you have to do is that so let's say this is set A, this is set B, and this is set C. Of course, this one right there, this triangle represents the universal set. Now, if I want to say shade union, all I have to do is that go to A, and wherever the reach of A is, I'm just going to highlight everything. So everything inside A, I'm going to highlight everything. I'm going to highlight everything. But it says A union B. I will go to B, and everything that B has, I'm going to highlight everything as well. So with this now, I've been able to do A union B. Don't mind me, I'm not supposed to do whatever is outside B. So union is just for you to just pick the individual sets, pick them one after the other, and just shape them. So union, it doesn't matter where they are touching, where they are overlapping, you just shade everything like that. So that is how you identify union of two sets. Now, if it is three set as well, if C was involved now, you just include C in your shading, and that's all. Now, the next is intersection. See, for intersection, this is how I usually teach it. So let me paste this again so that I can use it. Let me put it here. Okay. So to do intersection, I'm going to come back to this particular image here. So let's say I want to do A intersection B. So if I want to do A intersection B now, A intersection B. So what I'm going to do is that I'm going to pick a pattern for A. So let's say A is going to be, I can pick this pattern for A so that I'm going to be using vertical strokes. And I can pick a different pattern for B. I can be using horizontal strokes. Horizontal strokes. So therefore, when I'm done with A intersection B, I'm going to have this checkered pattern. So that's what I will watch out for. So let's go to this now and let's identify that. So we know that this is A, this is B, and this is C. So let's do, for everywhere we see A, we do the vertical line. So A, permit me to just do it like this anyhow. So these are the vertical lines for A. Now for B, I'm going to be using the horizontals, 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 horizontals. So now you look at where we have the checkered pattern. So we have the checkered pattern somewhere around this region now. So this region where we have the checkered pattern is where we have A intersection B. So, but my diagram is not really perfect, so it's not looking exactly how it's supposed to be. So I'm going to have to come in. I'm going to have to redraw that. So let me redraw that because my diagram is not perfect. So let's say we have A, we have B, and we have C. Yeah, I think this makes sense now. So A as the vertical, and okay, yeah, I think it's not bad. It's not bad. Just that it's not leaving a particular space that I want it to leave here. So A, we used the vertical. A, we used the vertical. For B, anything that anywhere we see B, we use the horizontal. We use the horizontal. So you can see the region where this is covering. This region here is the region of A intersection B. What if I wanted to do A intersection B intersection C? I can choose another pattern for C. C, let's say C can have maybe, let's say, something of yeah, this thick thing. So if I redraw this now, so I have set A, set B, and set C. So this guy has the vertical. It has the vertical. This guy has the horizontal. And this guy is to be ticked. So you notice that the only place where I have these three things all together, the only place where I have them all together is at this spot right here. So this spot is going to be the intersection of those two sets. So, and that is actually the summary of Venn diagram. Okay, there's the last one, which is complement. So for complement, if you have complement of a set, okay, I think I can adjust this. Yeah, this is okay. Now, if you have complement of a set, for instance, if I say you should shade A complement now, so the first thing you're going to do is that identify A. Once you identify A, then shade every other thing that is not A. So this is my A. You can see the boundary. So I can just quote the boundary of A like that. So once I quote the boundary of A, then I have liberty to shade everything beyond the boundary of A. So with this now, this is the complement of A. So everything that belongs to the universal set but does not belong to A, as long as I'm leaving A alone. So that is basically what complement of a set. So once you know how to identify these three things, then you are okay. Now, the next one is the cardinality of set. What is cardinality of set? Like I've said, cardinality of set is actually the number. So I mentioned it earlier when I was talking about power set. Cardinality of set is the number of elements that are present in that set. For example, what's the cardinality of set A here? It is 3. Of set B is 3. Of the A union B here, it is 5. So the number of elements that are present in that set is what? Is what we call the cardinality of such set. In B1 here, the cardinality of set B is 1, 2, 3, 4, 5. So this is 5. This is 3 as well. And so on like that. The cardinality of B2 here is 4. So cardinality of a set is basically the number of elements that are present in a set. Of course, I know that there are real life survey problems. We will be taking survey problems in another video. So if you have such questions, that means that if you have watched the class up to this point, so if you have such questions that you need me to answer, then you can always send it to me through the community. Then I will make a video answering them as a form of practice problem. So these are everything that you need to know about sets actually. And this ends the class for today. I'll see you in the next one. Don't forget to like, comment, and subscribe to the channel if you have not.